Hello everyone, welcome back. So today we are tackling a key concept, that is converting the regular expression directly to DFA. As already we have seen that converting RE to NFA, then NFA to DFA and DFA optimization. But here we can convert directly an regular expression into deterministic finite automata. So see, now this process has become foundational because regular expression, as we all know, describes the patterns in strings, okay, and DFA will help us in efficiently recognizing these patterns. To simplify this process, we'll go over some basic and essential concepts that are the four important functions: nullable, first position, last position and follow position, which will form the base to solve this, that is a conversion of RE to DFA using this method. See, this term may sound a bit technical, but they will make a conversion process clearer and help you understand that how DFAs are derived from the regular expressions. Okay. See, let's start with the nullable. See, this term tells if that a given node in our syntax tree. See, in this conversion, we will deal with the syntax tree. This process revolves around the syntax tree. Okay. So let's start with the nullable. See, this term tells us that if a given node in our syntax tree for the regular expression can represent an empty string. Okay, that is, we have a regular expression such that null string is also accepted. For example, I have A star. Okay, so it represents 0 or more occurrences of A, so null will also be accepted. Okay, therefore this star operator is always termed as a nullable operator. Okay, see, if a part of the regular expression can match without consuming any characters, okay, then that node is said to be nullable. See, these definitions can be asked here. I'm not writing the definitions here, but you can note down. For an instance, let's say in the expression A or null. Okay, A or, I have some expression like this, A or null. So it includes this null operator, or you can say epsilon or empty string, then the expression is said to be nullable. Next we have the first position. See, this refers to the positions in the syntax tree where the first character of a potential match can be found. Okay, see, think of it as an initial position or starting point in the expression which can match the part of the string. For example, I'll say there is a regular expression A B star. Okay, so the first position will be the position of A. Okay, as it is the starting point of any match. Okay, whenever you are going to match this string, the first position will be the position of A. So that is what your first position, because in the syntax tree, see here, this will be the first position of A. Okay, now there is a last position. See, this is, as you might guess, the ending position of a match in the syntax tree. So last position tells us that where the last characters in a match can appear within the tree. Okay, so see, in the same expression AB star, the last position can be any occurrence of B. Okay, it can also be null, even null. It can also be B or B. Okay, but it will always be B, right? Because B star can repeat multiple times, so extending the match to the last occurrence of the B. Same way, let's go to the follow position. See, this is a bit more involved. It tells us that the positions can immediately follow a given position in the syntax tree. For example, I have some position, last position of A and first position of B. Okay, so the follow position of this will be, A will be what? The first position of B, because it is followed, right? See, there are different rules for calculating the follow position, and we'll calculate the follow position only for the star operator and concatenation operator. Okay, we'll see. I'll explain you later. See, while we are constructing a DFA, follow position will help us by providing the connections between the states. Okay, when you know that which node is going to be followed at which position, then you can construct the DFA easily. So for example, I have a regular expression, let's say AB. Okay, so it indicates that the follow position of A will be what? Position of B. That is indicating that the B directly follows A in the language, which is described by this regular expression. Okay. See, don't worry if you don't understand. These terms are simple. Just go through the names, they will suggest you the meaning, right? And if you don't get it right now, you'll clear yourself when we go through the examples, okay? And we will calculate this positions. Okay, so let's first see the rules to calculate the follow position. See, the follow positions are calculated by for operators, for two operators. First one is concatenation. See how the follow position of the concatenation operator can be found. So let's say if n is the concatenation node, okay, let's say the position is n, such that it has this C1 and C2. So these are its child nodes, okay. This is basically a part of the syntax tree. I'm not drawing the whole syntax tree, just to make you understand that how the follow position of the concatenation operator is being determined. So let's say if I is a position in the last position of C1, okay, so here is an I is the last position of this C1. So then all the position in the first position of this C2 will be the follow position of I, right? Okay, so we'll follow this symbol. Okay, just remember this symbol. I'll explain you with an example, but here we are just clearing the rules so that we understand how we are calculating it in the examples, okay? So see, it is obvious something which is following will always be the follow position. So whatever is in the first position of this C2 will be the follow position of this last position of I. So let's say the follow position of I, follow position of n will be what? Last position of I union first position of C2, right? Similarly, let's see star operator, right? A clean star. So if n is the star node, okay, and I is the last position of n, let's say this is my node, okay, this is, let's say C1, okay, and it is in the position I. So then all the position in the first position, see here it goes like this. Okay, so let's say here there is some first position and here it is a last position. Then the follow position will be union of this both. Okay, let's see with an example. First, before that, we'll understand the rules to calculate the first position, last position, and whether it is a nullable or not. Okay, and for that I have just created the rules for the table. Okay, it is given in the book also. You will get it anywhere. See, let's first start with the leaf node. Okay, if there is any leaf node, let's say this, okay, and it has some another syntax tree, okay, but this is the leaf node. Okay, then it is obviously a nullable because it accepts the string null. Second is leaf node, which is labeled by some position I. Okay, now a node which is at some position I, it is obvious that it is not going to accept the null string. Okay, because if it was about to accept the null string, then it wouldn't have been at the position I, right? So it is false. Next is, see, the calculation or the, you can say, derivation of this first position and last position and the follow position, and these rules are mainly applicable to the operators. Okay, because while we are dealing with the operands, it is very simple. Okay, the position which is in the like before the operand, it becomes it's the first position, and the position we assign to the syntax tree becomes their first and last positions. Okay, so we don't follow any rules for the operands, and all the rules we are seeing here is for operators. So for our operator, we need to check whether this OR operator is nullable or not. Then what is the rule? That first we need to check whether C1 is nullable or C2 is nullable. Okay, if one of them is nullable, then this operator is said to be nullable. Same way, first position of n. When you are calculating the first position of n, that is this node, OR operator node. Okay, then you need to calculate the first position of this C1, then first position of C2, then doing union will give you the first position of this OR operator. Same way for the last position. For first you need to calculate the last position of this C1, then last position of C2, and you will get the last position of this OR operator. The next one is concatenation operator. Okay, for the concatenation operator, when you are going for nullable, okay, see, you know concatenation means appending the regular expressions, or you can say any inputs symbols, or you can say strings. Then when you need to check that whether this concatenation operator is nullable or not, then you need to do and that is obvious. If this is nullable and this is nullable, then and then only this is going to be nullable. Okay, if one of them is not nullable, then this operator is also not nullable. Next rule for the first position, for calculating the first position of this dot operator is, see, first we need to check if the C1 is nullable or not. If we find that this C1 is nullable, then we will do the union of first position of C1 and first position of C2. Else, if this C1 is not nullable, then the first position of this dot operator will be first position of C1. Okay. Similarly, while finding the last position, if my C1 is nullable, then the last position of C1 union last position of C2 will be this. Okay, else the last position of C2 will be the last position of this operator. Okay, see, understand one thing. If there is an expression like this, okay, and this is not nullable, then you can already see that the first position of this will be the first position of my regular expression, that is this operator, and last position of this will be the last position of this dot operator. So that is what we have done here in the else part. But if it is nullable, okay, then I am going to have an empty string also, and therefore I need to do the union of the both first positions and both last positions. Understood? Now let's go for this OR. Okay, see, a star operator. For star operator is always going to be nullable. Okay, so it is nullable. Then when we are calculating the first position, so it is obvious that first position of C1 and last position of C1 will be the first and last positions of this n, that is my star operator. So these were the rules which we have seen for calculating the first position, last position, and follow positions. Okay, so after understanding this, let's start with an example, or you can say conversion. First, I'll explain the steps for converting a regular expression to DFA. See how the regular expression is converted to DFA. So the first step is we need to construct a syntax tree. Okay, so first you need to construct a syntax tree, which is an essential step. In the second step, you need to find nullable nodes. Okay, just check what are the nullable nodes present in the syntax tree. In the third step, you need to calculate the first position of both operands and operators. Similarly, you need to calculate last position of both operands and operators. In the fifth step, you need to calculate the follow position of all the nodes. Okay, and in the last step, you need to draw you need to calculate the transition table, or let's say DFA with, or say using transition functions. Okay, so from using the transition functions, we will calculate the transition table, derive the transition table, and from the transition table we will draw the DFA. Okay, then let's understand the steps using an example. See, I'll take the example as A or B star, A, B, B and hash. See, hash is not considered as operator or something. It just denotes the ending point of this regular expression. Okay, I have just written here or like this. You can write this also. Okay, see, this is a standard example which have already been asked in your G2 examinations, and this is being explained in many of the books also. Let's start with our step 1, that is constructing syntax tree. See, here only the syntax tree is constructed from left to right. Okay, don't use this logic while constructing the leftmost derivative and rightmost derivative trees. Okay, we'll discuss in the parsing chapters although, but the technique used here to construct the syntax tree is different. So first we need to scan from left to right. So what is this? A. So A, then or B. Okay, then what it is? Star. So this is clean star. Then what we have to do? Concatenation with A. So we'll do concat with A. Then we'll do concat with B. Concat with B. And then again concat with B. And again concat with this hash. Okay. Now let's assign the position to these nodes. Okay, see, I'll assign this as 1. I'll assign this as 2. Then 3, 4, 5 and 6. Okay, our second step was to find the nullable node. The only nullable node here is what? This star operator. Okay, so we'll mark this star equal to nullable node. Okay, our third step was, so this step 1 and step 2 is completed. Let's go with step 3. Step 3 was finding the first position of these operators and operands both. Now see, whenever we are calculating the first position of operands, it is always the positions that we have assigned to them. So we'll write the first position here, 1, 2, 3, 4. The first position of this B will be 5 and this will be 6. Okay, so this is the first positions of the operands. Now let's calculate the first position of the operator. Okay, I have already discussed the rules here. See, the first position of the operator, this OR, can be calculated by how? First position of C1 union first position of C2. So what is the first position of C1 here? 1 and 2. So 1 union 2 is 1, 2. Now this is the first position of this will be first position of C1, that is this. So 1, 2. Now first position of this concatenation operators, how we'll calculate the first position of concatenation operator? So we'll check if the nullable C1, so we need to see here if C1 is nullable. Yes, our C1 is nullable. So the union of these first two positions, that is 1, 2 and 3. Now let's go to this operator. So you need to check C1 and C2. C1 is nullable? No, C1 is not nullable. So what we need to do? The first position of C1. See here. If nullable C1, then this. Else we have to take the first position of C1. As C1 is not nullable, we are taking this as 1, 2 and 3. Same logic will be applied here. 1, 2 and 3. And here also 1, 2 and 3. Then our step 3 is completed. Now go to the next step. So now calculate the last position. So how will calculate the last position of the operands? It will be same. So 1, 2, here will be 3, 4, 5 and 6. Okay. Now let's calculate for the operator. See, the rules for the operators will remain same, that is last position of C1 union last position of C2 for this one. So last position of C1 is 1 and last position of C2 is 2. So 1 union 2 is 1, 2. See, I am writing here directly in the diagram, but you need to write it here. See, I'll just explain for the first position. So you can write here that for operands last position of n is equal to position of n. Okay, therefore last position of 1 is equal to 1. You can write this same way for last position of b, you can write as 2. Similarly, you can write for all other operands. Let's say the last position of c is equal to 3, then last position of a. Okay, similarly you need to write it for first positions. Okay, so first position of n is equal to position of n. So this is for operands, and when you're writing for operators, you need to draw the subsections of this syntax tree. That is, for example, if you are writing for an OR operator, that is a and b, right? So the first position of OR is determined as first position of a union first position of b. Okay, so let's start with the last position of this star operator. Okay, so the last position of this operator will be last position of this c1, that is 1, 2. So 1, 2, right? So this was last position of c1. Now let's calculate the last position for this. Okay, so now let's calculate for this operator. For calculating for this operator, first we need to check if there is a nullable c2. No, our c2 is not nullable. So what will be the last position? Last position of c2, that is 3. So our last position of this operator will be c, that is 3. Now let's see the last position of this. So first we need to check if nullable c2. No, then the last position will be 4. Similarly here there will be 5, and here it will be 6. Okay, now let's go to the step number 5, that is calculating the follow positions. See, for calculating the follow position, we'll calculate the follow position for every node, that is 1, 2, 3, 4, 5 and 6, and here we will have the follow position. See, the table of this follow position is very important because we will use them in transition functions in the last step. See, now calculating the follow position for node 1. Okay, so for calculating this, for this follow position will be what? See, we calculated the follow position for concatenation and dot operators, right? So for example, first we'll start with this star operator. For star operator, our follow position is, we have already discussed the directions. Our follow position was what? This, right? That is first position and last position union. Okay, so we'll follow the same thing, that is this. So 1, 2. So similarly for the follow position for 1 and 2 will be 1, 2, 1, 2. Okay, see, don't, if you're not getting anything, just take care of the directions. Whenever you are encountering star operator, take this direction. If you are encountering dot operator, take this direction. Okay, in the star operator we have done this. So for 1 it is 1, 2, and for 2 it is 1, 2. Okay, therefore we have written 1, 2, 1, 2, and for 2 also it is 1, 2. Now when we are doing for this operator, okay, we need to follow this directions. Okay, so for 1, 2 and 3 it is 3. So what we'll do for 1, 2 and 3 it is 3. So we'll just write 3 here. Similarly we'll do for this operator. So for 1, 2 and 3 it is what? 4. For this 3, that is for this operator, the follow position will be 4. For 3 it is 4, and for 4 it is 5, for 5 it is 6. So for 4 it is 5, and for 5 it is 6. Okay, so this is the way we have found the follow position. See, we will not get any follow position for 6 because it is nothing but the end of the regular expression. We have just used it for marking the end of the irregular expression. Now let's see the final step, that is DFA construction. See, now we have already found the follow position, first position and last position. Our first step in constructing this DFA is, first is your initial state. See, the initial state of the DFA will be what? It will be the first position of root node. Okay, what was my root node? Root node was nothing but this. So what is my first position? That is 1, 2 and 3. So I'll give it as 1, 2 and 3. Okay, so this will be my initial state. Let's mark it as A. Our second step will be to calculate the transition function of A. So my input symbols are A and B, so I'll calculate the transition functions with A and B. See, while calculating the transition function of A and B, we use the follow positions. Okay, now see, in A what I have 1, 2 and 3. So I'll go for 1, A, 2, A and 3, A. Okay, now let's see here. In the syntax tree, just check. For 1 there is A, yes. For 3 there is A, yes. For 2 there is no A. So we'll consider 1 and 3. So what you need to do is just make this 1, 3 into one group, and now make the union of follow position of 1 union follow position of 3. And you have already found the table of the follow positions. Determine the follow positions from that table, and you will get the follow position of 1 was what? 1, 2 and 3, and for follow position of 3 we had 4. So you will get 1, 2, 3 and 4, and mark it as B. Okay, name the states. Similarly, find this A, B. So what we have? 1, 2 and 3. So just go and check. For 1 is there any B? No. For 2 it is there, and for 3 there is no. So we'll just mark 2. So what will be the transition function? That is follow position of 2. So you have got the table. From the table, the follow position of 2 is what? 1, 2 and 3, which is similar to which state? A state. So we'll mark it as A. Okay, similarly you need to find it for B now. So for B, this is B. You will need to find B, A and delta B, B. You will get it as follow position of 1 union follow position of 3. I am doing it directly, you can just refer here. See, for B what I had? 1, 2, 3 and 4. So for 1 I have A, for 2 I don't have, for 3 I don't have, and for 4 I don't have. So what I'll do? 1 and 3. So I have already taken 1 and 3 follow position. Similarly you can go for B, and you will get it for B is where? 2 and 4. So you will get follow position of 2 union follow position of 3, and this will give you 1, 2, 3, 4, and this will give you 1, 2, 3 and 5. So you can name this you have got as new state. Okay, this already exists, that is B. So you need to find it for C. So delta C, A and delta C, B. So you will get delta C, A as follow position of 1 union follow position of 3, which is nothing but B itself. Okay, and similarly for C, B, you will get, see, the new state is 5. Okay, so 1, 2, 3 and 5. For 2 it was B, and for 5 it is B. So we'll get 2 and 5. So follow position of 2 union follow position of 5, and you will get it as new state, which is 1, 2, 3 and 6. Let's name it as D now. So you need to calculate transition function for D now. So delta D, A and delta D, B. You will get delta D, A as follow position of 1 union follow position of 3, which is nothing but B. And similarly you will get the transition function of D, B as, let's see, D is what? 1, 2, 3 and 6. Okay, D is what? 1, 2, 3 and 6. We don't consider 6 here because it doesn't have any A or B as an input transitions. So only 2 will be there. So follow position of 2. What was my follow position of 2? That is 1, 2 and 3. So it will be follow position of 2. That is nothing but 1, 2 and 3. And what was my 1, 2 and 3? A. So this is A. Now see, from this transition we'll make a transition table here. Transition table. It will contain the states and the input symbols. Okay, now see, my state was A, B, C and D, and from the transition function of A to A give me which state? That is B, right? From A to B I got A state. Then similarly for B I get B and C. Then for C I got B and D, and then again B and A. This was my transition table. Now from transition table we can construct a DFA. See, my initial state is what? A. So I'll mark this as an initial state. Then from A as an input symbol we can go to B, and from A to A we can go by B as an input symbol. When we get B, A as an input symbol to B, we can go to B itself, so that is B. And when we get C, from B, so from we can go from B to C with B as an input symbol. Then from C to B using A as an input symbol. From C to D using B as an input symbol, and from D to B using A as an input symbol, and to A using B as an input symbol. So this is my DFA. See, now DFA is incomplete without marking the accepting state or final state. So for marking the final state or accepting state, remember the position of this, okay, because it marked the end of the regular expression. So wherever the position of hash occurs, in whichever set will be your accepting states. Now just check that at where the 6 appears, so that is D. Okay, so D will be my accepting state, so mark it as D. So with that we have covered the conversion of RE to DFA. So this method has given us a structured approach to grow from the regular expression to our fully functional DFAs, right? So converting these expressions was a huge part of lexical analysis, as it makes a patterns recognition both precise and fast. In our next session, we'll move to the parsing theory, because this chapter has come to end with this conversion, which is another exciting area in the compiler design. So, and this parsing theory will focus on analyzing and structuring the syntax. Okay. So if you have any questions about any of the concepts that we have covered so far, feel free to drop a comment below. In the next session, we'll start an exciting new chapter, that is parsing theory. Till then, bye. Thank you.